So hopefully you did a free body diagram to start it off, right? Or at least a force diagram. I'm going to have T and T. We'll have mg and my acceleration is going to be in that direction. Right? And then, of course, I have the child in circular motion here. So if I was to draw a picture of the child, they're moving like that, with the radius being our 2.99 meters. Right? So in this case, the tensions are providing the force needed for this upwards acceleration. So really I'm doing some of the forces is MA, using Newton's second law here. I have 2T minus mg equals m times v squared over r. Because of the circular, to be in the circular motion, you need that acceleration, right? And we're assuming, let's see, all right, yeah. So now just substituting in, we're looking for v, right? So I'm going to have 2t minus mg all times r over m square rooted equals v. Substitute in 2 times, I think mine was 347 newtons. All right. Do I need to go further, or do you think you got it from this point? Huh? You think you're good? Okay. I won't even go into that. So what mistakes did people make? Two chains. Was that the main mistake? Okay. All right. Back on recording. So, looking at number 10. With the child on vacation lying on her back. Out the motel window. Screaming and sliding down. Feet first down. Terminal speed of 6.5, riding high on the outside wall of the horizontal curve. So what does it mean by riding high on the outside wall of a horizontal curve? You can assume that she is, yeah, right at it's vertical, not at some angle. To try to simplify it for you. Find the tension in her muscle, in the muscles on both sides of her neck. So what they're adding in here is the idea that because she's going around this curve, there is going to be some additional forces on it. So at the beginning here, we have her head, and to raise it, they have to provide a force each of 50 newtons, right, to raise her head up. So really 100 newtons. So that's kind of telling you how massive her head is. It's one way to look at it, right? All right, because the tension of the muscle on both sides of her neck is 50 newtons. She's from Minecraft. Come on. So now, going around this curve, she's here, and I'm just drawing my force diagram is of her head, right? She wants to keep going straight. So now there has to be a normal force acting in on her, right? And she's now accelerating in that direction. But that weight of her head is now, whether we take it to be 50 or 100 newtons, is now in this direction, down, rather than in the direction she needs to move her head, right? It is a weird concept. So what we're looking at is we're going to use the 50 newtons to say, well, therefore, 50 newtons equals the mass per head times g. So 50 newtons. Actually, we're not going to use 50 newtons. We're going to use 100 newtons. As they say, the muscles on both sides of her neck. So not 50 here, but 100 newtons. Ed, what did you figure out the well, unless they're thinking 50 newtons total, then that would be the average size of the human head, right? Because 50 newtons would be just a little bit over 5 kilograms. Yeah, that's where I'm thinking it's combined. They gave her a really big head. Okay. Oh boy. So again, Newton's second law here. Only force in the centripetal direction is the normal force. That's giving our massive head girl the acceleration, which is going to be v squared over r. Again. So what do we ask? The force normal. So this is going to be 100 newtons over g. And my V was what, 6.5, I think? 6.05. Yeah. I'm less confident of this one than the last one. Because it is Monday after all. Day physics doesn't work. And we're actually going to look, we actually want our answer. We want to know, I think it's going to be Fn over 2. That's the 2.4 meters. That's the radius of my curve. So I'm going to pause the video just to see if it, our problem is ignoring this, that 50 newtons, or that 100 newtons. I think we're at 50 newtons. So the actual force that her neck has to exert is going to be in this direction, where it's going to equal F squared will equal the force normal squared plus, here I'm calling it 50 newtons squared.
So she has to keep it from going down as well.
Yeah. And so but let's use that 100 newtons rather than the 50. Because I think that's the better. This would be 100 newtons here also. So we're going to leave are, what is it, 100 newtons over G times 6.05 meters per second squared over 2.4 meters. Run out of room, plus 100 newtons squared. Let's see how this goes on Monday. So I think that's what we forgot.
Can you divide the normal force by 2 again?
And then we're gonna find F over 2 in the end. Let's try it. Let's make sure. So, huh? So we do have the weight per head as in my case as 100 newtons plus the force needed for the centripetal force, and then that. Yeah, don't forget. I know my work is really, really messy. I'm sorry about that. So basically, what we're doing is I'll write it up here. The force that we're looking for that's provided by her neck, we're calling F. And that is a combination of the two components, the normal force and the weight of her neck. So it's having to provide those two. Since they're at right angles to each other, we can use Pythagoras to say, well, the force provided by the neck squared equals the normal force squared plus the 100 newtons, which is the weight of her head squared. The normal force is what is providing the centripetal force. It's providing a force in the centripetal direction, and so that is over here, our mv squared over r. M being the weight of her head divided by 2, pi g. This is, let me see yours. Let me pause. The expression blah, 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 gives the magnitude of the resistive force in newtons exerted on a sphere of radius r meters by a stream of air moving at speed v with a meter with appropriate units. Suppose that their numerical values are this for A and this for B. Using this formula, I find the terminal speed of water droplets falling under their own weight in air, taking the following values for the drop radii. 10 micrometers, 100 micrometers, 1 millimeter. Note that for A and C, you contain accurate answers without solving a quadratic equation by considering which of the two contributes to the air resistance is dominant, ignoring the lesser contribution. Or you can just use your calculator to do that. Nice. Let me give you a note though. Force diagram right away, right? Weight down, force resistive up, acceleration equals 0, right? So we're looking for when that equals the weight. These are water droplets, and we know the volume of a sphere is 4/3 pi r cubed. Volume. Although, now I want to feel like I should look that up. That's the song. get to all the doodah. See what you did now, Matt's dancing.
I'm sorry. What did you say?
All right, so the mass is always going to be the density times our 4/3 pi r cubed, right? And so we're always going to have that the force resistive equals the weight. Our force resistive is AR V plus V R squared V squared equals density of water 4/3 pi r cubed times little g. If you notice, you have an r in every term, right? So you can bring this down to squared, bring that down, and get rid of that r. So you're left with AB plus BR V squared equals rho 4/3 pi r squared g. Personally, at this point, it's just algebra. You know, this is where I would use the capabilities of my TI to either put this in the solver, leaving A and B as variables. Sorry, leaving R as a variable along with V, and then plug in my values for R, and it'll give me a different V every time. Or, you know, solving it. Some of you I know like to use graphs on your calculators. Some don't. All right, depending upon the model you have. Remember, if you have if you have the older model, you need to rearrange this to solve it for 0 before putting it in. All right, but now it's just algebra. Yeah, I would work everything in meters. I'm going to let you research that on your own, so hopefully it will stick in your brain this time. But I think if I tell you, I may be enabling you. The metric units. 1 kilogram per liter. And you don't want it in liters, you want it in meters squared. Because you want your R in meters per second squared for your G or newtons per kilogram. So your rho is going to need to be in kilograms per cubic meter. You know, you can do that in your calculator too, you know? Yeah. On your calculator, if you go to apps and then find your way to SciTools, which may be the hardest part, depending upon how many apps you have. And it's even have it in French on there.
Have it in French?
Mm-hmm.
Thank God.
So you can go to unit converter. I went to apps, SciTools. Then someone has cleared the memory on yours. You should probably hook it up to a computer and re-download it. And here you have, let's see. Oh, maybe density isn't in here. Yeah, I'm not seeing density. But you could do volume, and you know it's, you want to, 1 liter is how many cubic meters, and it's 1 times 10 to the negative third. Oh, wait a minute. Huh? That's rho. That's the density of water, which is 1 kilogram per liter, and there's 1,000 liters in a meter cubed. So rho would be 1,000. There's no P. Rho. You both. No. Rho is the density of water, which is 1 kilogram per liter, or 1,000th of a kilogram per cubic meter.